Hello everyone. I have more awesome evidence of our flat Earth today. It's a new approach and it's quite clever. I'd like to primarily thank Dr. Michael Heffron for coming up with this novel test and for his excellent presentation and work here. I would also like to thank Space Audits for sharing this information. I'll have a link in the description to Space Audits where you can go and subscribe. Space Audits is an awesome channel. They've been covering the Knickerbein flat Earth proof extensively. I highly suggest you watch this video here. Also, Space Audits was on Globebusters last week, discussing the missing upward Earth curvature shadow flat Earth proof, which I'm very fond of. I'll have links to both videos in the description. As I understand, Dr. Michael Heffron will be on the Globebusters this Sunday, where they will go over the updated presentation that you're actually seeing right now. And hopefully, Dr. Heffron will be able to answer any questions you have and correct any mistakes that I might make. But I love this test, and I hope that many more of you will consider replicating this. However, I do think that you have to conduct this test at higher elevations in order to avoid atmospheric distortion and compression. This test was conducted with respect to Pikes Peak in Colorado, which is perfect with that 6,000-foot base elevation. The test was conducted at Dr. Heffron's house, which was 50.7 kilometers or 31.5 miles east of Pikes Peak. Here's a picture of Pikes Peak from his driveway. Pikes Peak has an elevation 2,226 meters or 7,303 feet higher than Dr. Heffron's location. Now, we're going to assume a flat Earth and use some trigonometry. I inputted the distance and Pikes Peak elevation, and you get an angle of 2.514 degrees, or 2 degrees, 30 minutes, 50 seconds. Dr. Heffron calculated 2 degrees, 31 minutes, so they are pretty close. In other words, if the Earth is flat, which it is, then the angle to the top of Pikes Peak from Dr. Heffron's location should be close to 2 degrees, 31 minutes. On a globe, the peak would be lower at 2 degrees, 17 minutes, because on a globe, the Earth would have dropped 662 feet at that distance. 31.5 times 8 inches divided by 12. Using a theodolite, Dr. Heffron obtained an angle of 2 degrees, 30 minutes. That measurement alone confirmed the Earth is flat, which is awesome evidence, but it gets better. Now, the globe propagandists are going to all proclaim in unison that Dr. Heffron got that flat Earth angle measurement due to Pikes Peak jumping upwards due to the miraculous curvature-removing properties of refraction. We've all heard the allegation hundreds of times, and that's where Dr. Heffron thought of a genius way of destroying the claim that atmospheric refraction somehow removed the curvature. Dr. Heffron was able to locate a star that dropped behind or was occulted by the top of Pikes Peak. Notice in the diagram that from his position, 51 kilometers away, the star must also be at the same angle of 2 degrees, 31 minutes right before it disappeared. Now, if Dr. Heffron was able to immediately teleport to the top of Pikes Peak, he would still get the same angle of 2 degrees, 31 minutes to the star on a flat Earth. Are you with me so far? For reference, here's a picture of the star that dropped behind the top of Pikes Peak. Dr. Heffron then used stellarium to get the angle to the star from the top of Pikes Peak. But this is the important part. Stellarium allows you to disable atmospheric refraction. The big question is, once you remove atmospheric refraction, would the star be in a straight line to the top of Pikes Peak down to the theodolite? Well, according to stellarium, once you remove atmospheric refraction, the same star had the same straight line angle at 2 degrees, 31 minutes. But the star would have been 15 minutes higher with atmospheric refraction. Because the star lined up with the peak, the Earth has to be flat. Now, the globe propagandists are stuck because they can't claim the mountain jumped up due to refraction, but the star somehow avoided atmospheric refraction and jumped down. I hope this little summary helps you understand the presentation. Enjoy.
Yes, keep it simple, stupid hypothesis. H1, Earth flat. H0, Earth not flat. That's why it's important to instead refute the null hypothesis, which must be carefully worded as the exact opposite of the hypothesis. It's important to ensure H1 and H0 are not merely opposite, but also mutually exclusive, so that if the null hypothesis is probably false, then the hypothesis is probably not false. Because H1 may contain hunches and or unstated assumptions, it can never be proven. For example, this and the prior drawing clearly illustrate the unstated assumption that flat does not mean free of hills and valleys. Instead, flat would be interpreted by most reasonable people as not the surface of an ellipsoid. It is not necessary to complicate H1 by stating it is not an ellipse, not a pyramid, not a square, etc., because if H0 is true for any reason, then H1 is false. However, if H0 is false for any reason, then H1 is probably not false. In other words, H0 asserts that H1 is wrong, and so the goal is to determine or to demonstrate that H0 is probably wrong. If H0 is probably wrong, then H1 is probably true. So if the H0 is the Earth is not flat, if we can prove that wrong, if we can nullify the hypothesis, it means that H1, the Earth is flat, is probably true. Now, because science is never settled, it is generally considered too strong a statement to claim that the hypothesis is probably true. So instead, we assert to some level of confidence that H1 is probably not wrong. Refer back to Ether Roundtable number 63 if you need more than this brief overview of the need for a null hypothesis. Conveniently, this is a view of the Rocky Mountains from my driveway. The highest mountain peak in this photo is the snowy Pikes Peak at the top center of the photo. One moment. All right. Simple trigonometry should be adequate to refute H0. Uh-oh, he's pulling out the theodolite, boys. In theory, simple trig should be sufficient to refute H0. You got a 50.7 kilometer baseline, a 2226 meter elevation, results in a theta angle of 2 degrees and 31 arc minutes. This website calculated the distance between me and the peak, and the initial bearing from my longitude, and the final bearing from the peak's longitude. The final bearing will become useful a few slides from now. Now, Pikes Peak is 50.7 kilometers from me, and it is 2,226 meters higher than my altitude. Because of that, simple trig says that a theodolite should sight the Pikes Peak visitor center about 2 degrees and 31 arc minutes above a flat plane through my altitude. So using plain trig, we got 231. Not going to be the same for spherical trig, if you didn't know that. Now, the David White 8300 theodolite is what he used. He says, I found a well-used antique David White 8300 theodolite on eBay that cost me $65, including free shipping. Now, that's a steal, bro. Many people claim this model is the best theodolite ever made. To anyone who may be interested in buying one of these, I recommend paying extra to get its original tripod, because it's got a very non-standard tripod and it needs an expensive adapter to attach it to a modern tripod. It's slightly tricky to operate because of its many adjustments, but there's some good YouTube videos out there to show you how to use it. All right. Now he's got this vernier scale on it. This is just showing how it works, how is the precision of his measurement, right? So it's also slightly tricky to read due to its vernier scale, but the YouTube videos can help with that too. To get accurate measurements, it's necessary to first adjust the theodolite, according to what he writes here. Basically, it's the vernier scale on the bottom is accurate to the nearest 5 arc minutes. So to the nearest 5 arc minutes. All right, so that's the precision that we're working with. Plus or minus 5. This is a close-up of the visitor center on top of Pikes Peak. The summit's very flat, and the visitor center is easy to identify from far away using a telescope or a theodolite. At night, the observation room on the far left is lit and is therefore easy to identify on the mountaintop. Here's a photograph. Oh, you got it up there. Visitor center is 4,300 meters, 50.7 kilometers from me at 2074 meters. So the flat Earth elevation angle is 2 degrees, 31 arc minutes. Pretty simple. He couldn't get a good photo through the theodolite, so he took it with his telescope. And he got the altitude, latitude, and longitude from Wikipedia, altitude, latitude, and longitude of the theodolite from the GPS Waypoints app on his Android phone, which is accurate to within about a meter at least, right? Modern GPS. So that means the elevation of the visitor center should be 2 degrees 31 arc minutes above my level if Earth flat, or 2 degrees 17 arc minutes above my level if Earth globe. For H naught to be true, Earth not flat, the elevation needs to be something other than 231. My theodolite measured 230, which was the closest its accuracy would allow it to get to 231. Thus, to within the accuracy of my theodolite, my very first measurement refuted the H0 assertion that the Earth is not flat. That is only one data point, but there are many more to come. Now, it gets better, right? Because this is just a raw theodolite measurement, and there's stuff like refraction that affects what you see. So he's got the refraction formula curve here. As we all know, critics will claim that the Earth only looks flat, and that's due to atmospheric refraction. Well, that correction for refraction conveniently elevates the globe Earth prediction of 2 degrees and 17 arc minutes to 2 degrees 32 arc minutes, which is consistent with my actual measurement to within the accuracy of my inexpensive theodolite. What an amazing coincidence that atmospheric refraction accounts for the difference between flat and globe. To refute H0, I really need a more accurate theodolite. But then, critics will just claim that local gravitational anomalies will skew the imaginary sea level plane between me and Pikes Peak. And if I get an even more expensive theodolite, critics will then claim atmospheric distortions are skewing my measurements. So rather than refuting their own null hypothesis, the critics want to argue about why my null hypothesis should not be rejected as false. Don't let them do that. You can reverse the hypotheses. You can say H1 Earth globe, H0 Earth not globe. If they don't like my null hypotheses, the critics are free to reverse H1 and H0 or develop their own and then try to demonstrate the falsity of their own null hypotheses that Earth not globe. How would they go about falsifying the Earth not globe null hypothesis? Photos are not very convincing when compared against precise theodolite measurements. Equally unconvincing are the many correction factors that they need in order to explain why the measurements demonstrate their H0 is true rather than false. They would need to modify their hypotheses to claim that the Earth measures flat only because local gravitational anomalies cause level to be skewed, or because light is bendy and surface refraction makes the Earth measure flat, or because atmospheric disturbances make it measure flat, or because mirages make it measure flat, or a combination of all those factors. How convincing is that? Looking at things from their perspective helps to highlight the absurdity of their arguments. Well, what can we do? Ooh, we could use a celestial theodolite. What does that mean? We can do better. Both flat and globe Earth advocates agree that the position of the stars in the sky is precisely known. Although, globe Earth advocates will argue that atmospheric refraction near the horizon makes those stars appear higher in the sky. So let's assume for a moment that atmospheric refraction is a myth designed to explain away the absence of the curvature of Earth. If that's true, then an observer on flat Earth and an observer on a distant mountain peak would measure the same elevation along the same straight line of sight. If you imagine instead that a globe Earth is curved, so the peak tilts left and the telescope tilts right, then theta on the peak will be larger and theta at the telescope will be smaller. Assume that he's talking about left and right based on drawing a circle, of course. 2D projection of the Earth. Assume that I'm observing Pikes Peak, occluding stars from my house. Since the flat Earth elevation of Pikes Peak is 231 from my sunroom, then an observer on top of Pikes Peak should observe the star at that same 231 when it vanishes from my view. I set up my C-Star S50 telescope for 1 second time-lapse and 1 second exposures. That configuration produces 2 seconds of 30 FPS video for every minute of sky watching. At that frame rate, every video frame represents a quarter of an arc minute of stellar motion. Okay. Telescope. Watch the mountain peak occlude stars. We can defeat the globers using their own tools, sorry. Telescope. Watch mountain peak occlude stars. Stellarium. Set location in stellarium to the peak. Turn off atmospheric corrections. Read elevation of star from the stellarium display. This is the point where it is wise to defeat the globers using their own tools. That puts them into the position of having to argue their own tools are no good in order to refute your results. Wow. Stellarium's a popular astronomy tool that's a free application for my Chromebook. With proper configuration, Stellarium shows the elevation of a star when the peak occludes it at my location. By default, Stellarium uses atmospheric refraction, so it's important to click the atmosphere icon to disable that correction. That's important because falsifying the null hypothesis depends on real measurements rather than measurements corrected for refraction. It's also important to set the location from which Stellarium views the sky to the mountain peak, because it assumes you are on a globe and modifies the elevation angle accordingly. That will allow you to easily determine whether the uncompensated stellarium elevation for the star is in line with your view of the peak. Trigger warning. The following results may cause globers to melt down. The remainder of this presentation may cause cognitive dissonance for those who believe the Earth is a globe when they realize their own globe Earth tools clearly indicate the Earth is flat. Oh, is that the star 39 Aquarii being occluded by the mountaintop? The time-lapse video was 2 minutes of viewing the Pikes Peak Visitor Center 50.7 kilometers west of my house. A jet flew from south to north about midway through the video, but this was my first relatively good shot of a mountain peak occluding a star. The photo on the right is the video frame 1 second before the Pikes Peak Visitor Center occluded the star 39 Aquarii at 6:27:25 p.m. on January 31st, 2025. The white rectangle on the left side of the peak is the lights in the observation room of the visitor center. There's a light dusting of snow on the peak that's visible due to the starlight from the clear sky above. The light gray circle is the stellarium view of a 15 arc-minute radius around the approximate midpoint of the ground level of the Pikes Peak Visitor Center. The dotted red line is the expected elevation of 39 Aquarii. So it was about 2 arc minutes higher than expected. 15 arc seconds, 1 clock second, of that is because the visitor center had not yet occluded the star, and another 15 arc seconds was due to the height of the visitor center above the ground. Thus, the actual deviation from the expected measurement was about 1.5 arc minutes. Okay. According to Stellarium, Pikes Peak occlusion elevation. For the star, it would be 2 degrees, 46 plus or minus 2 arc minutes with correction. And without a correction, it would be 2 degrees, 31 plus or minus 2 arc minutes without a correction, right? He measured 230. He got 231 plus or minus 2, which is within that range. Now my sunroom occlusion elevation, 219 plus or minus 2 with, and 204 plus or minus 2 without correction. So from the top of Pikes Peak, Stellarium says that the occlusion elevation of several dozen stars was 246 plus or minus 2 with correction and 231 plus or minus 2 without correction for atmospheric refraction. From my sunroom, Stellarium says the occlusion elevation of those stars was 219 plus or minus 2 with, or 204 plus or minus without correction. So for the uncorrected elevation of those stars when viewed from the top of Pikes Peak, the dark red values are a 3 sigma match to the flat Earth calculated values, thereby accomplishing my goal of rejecting H naught. Because remember, he pointed it at the mountain peak, which was also the place where the star was occluded, and it was occluded and measured at 230 plus or minus 5, because that's the precision of his instrument, right? So he got 230, and it happened at 231. Now, according to Stellarium, he should be seeing the elevation of that star at 219 with atmospheric refraction, or 204 without. So how is it that the mountain and the star lined up to occlude one another at the same elevation of 231, which is non-corrected for the star, but is corrected for the mountain when we talk about in terms of refraction for a glob? He's literally saying that he got the, using no correction factor and using FE plane trig, he got the predicted angle for the mountain and the predicted angle for the star, and they overlapped perfectly, and that's the exact moment the star was occluded by the mountain.
What a legend.
If you were to use glob, right? If you were to use glob, then without correction, they should be about 30 arc minutes apart, or half a degree apart. Rough. My level of confidence for those measurements is about 3 sigma, which is in the neighborhood of some of the best doctoral dissertations. Perhaps Pikes Peak is just an outlier. So let's move on now to another mountain peak. And he's got a list right here. Recent cloudy skies have prevented me from collecting this data, but Blodgett Peak is to be determined soon. Man.
Excellent reading, Piezo.
Man, I draw a straight line from the ground to the top of the mountain to the star, and they all line up. And that only works on plane trig, because if you try to use spherical trig, they have to be in different locations and have different angles.
Yep.
Crazy.
Man.
GG, Globe. It's been real.
Excellent.
Gotta adjust the null
reading,
hypothesis. That's a great read, bro.
Is he
Thanks.
saying the theodolite readings don't match up with the stellarium readings?
No. What he's actually saying is that if he uses the theodolite reading from his position and assumes flat, and then compares it to the stellarium readings from if he was on top of the mountain, they match up to draw a straight line from ground to mountain across the mountain peak, which only works if flat.
So he's saying the theodolite reading is accurate?
Yeah.
Okay.
Plus or minus 5 arc minutes, because the precision of his instrument's only down to plus or minus 5. But he got 230. Plane trig says 231. So it's like, he was off by 1 arc minute, and then plus or minus the error. But it should have been off by 15 if it was glob.
So basically, they say 2 degrees 17 arc minutes is the globe prediction, and then with refraction, they say like, oh, it raises that up to 2 degrees 32.
Yeah.
And that's why it matches the flat Earth prediction. That's what they say.
Correct.
But when you include the star in the same optical corridor, as you say,
Right.
then that the refraction calculation would bring the star higher, but it doesn't.
Right. Because all he had to do was time exactly the moment that the star got occluded by the mountain in his time-lapse footage and compare it to stellarium, and he can see precisely the elevation angle to the star in stellarium according to the Nautical Almanac and compare it to his theodolite measurements. So that's what he did. Man, they're going to hate this when we start using occultations, because that's like one of their favorite tools, is looking at the stars and saying, oh, blah, 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 we measured the transit of Mercury and Venus and blah, blah, blah. Occultation of Jupiter's moon and the speed of light and Neptune. And
So again, shout out to Dr. Michael Heffron.